OFC 2024. I'm Martin Rowe with EE World, and we are speaking with Adam Carter of OpenLight Photonics. OpenLight produces IP for transmitting light on top of silicon chips. I hope I'm getting that right. And
Inside the silicon chip.
inside the silicon chips. Okay, not on top. Okay. Adam, can you explain some of your technology and where it's being used?
Yeah, so what we do is through a foundry partner, which is Tower Semiconductor. We produce components that sit in a process design kit, PDK, that customers can access and design all sorts of different integrated circuits for very different market segments. We have customers in the datacom field, the AI/ML, in automotive LiDAR, as well as healthcare and sensing type of applications. The way it works and where we are differentiated from most other companies that have silicon photonics is we heterogeneously integrate the active components into the silicon as part of a silicon process. So how we do that is you take an 8-inch silicon wafer, you put in a layer of oxide, and then you define all the passive components, the waveguides, splitters, couplers, anything like that. And then you bond the indium phosphide laser material onto the waveguides in strips, and then you etch the material away to define the laser. Why that's important is because you get much more accurate coupling of the laser light into the waveguide. Typical coupling efficiencies of externally coupling lasers into silicon is around 30%. So you use 70% of the output power. With our process, you get 90% coupling efficiency, and that means you can drive the laser a lot lower drive current, which means the power consumption is reduced as a result of that. It then goes back into the fab and goes through a conventional silicon process. So more oxide definition as well as various metallization. So when you take a cross-section of the chip, it actually does look like a silicon electronic IC, except it has a block of the 3,5 material or indium phosphide for the laser section.
So you're actually passing light, as you said, inside the chip.
Correct.
And now, why is that? What advantage does that bring over using a more traditional semiconductor process, where you'd be using, which would be electrical?
It's different because you can miniaturize the actual functionality. So today, if you have a laser, you would need an isolator, you need lensing, and to couple it into the fiber or in through a standard LC connector. With our approach, everything is integrated on a piece of silicon, which is about 5 by 7 millimeters, which is actually shown here. If you can have up to 8 to 16 channels. You can scale that even further, but it would be a lot bigger if you were using discrete components.
I see. So what are some of the applications that you've seen? For example, I see this mostly in datacom, but are there other applications that can be where this technology could be used?
Yes, I mean, we're seeing lots of different applications, particularly in automotive LiDAR. There is a new technique called frequency modulated continuous wave LiDAR, which a lot of companies are looking for. One of the reasons why they want that type of LiDAR is because it enables you to see further away from a car than you can with the traditional approach of a time of flight type of solution. Our technology lends itself really well to that because we can put semiconductor optical amplifiers inside a photonic circuit, which then helps with pixel refresh rates and also with distance as well. So we're seeing a lot of companies very interested in coming in and designing those types of circuits with our PDK.
Very good. Thank you, Adam.